So if you look back to your applications with logs, we had a problem. It was number 3 on application part 2. We had a problem that said determine when an investment of $1,500 accumulates to a value of $37.50 if the investment earns a rate of 8% compounded monthly. So we came up with a formula. We used your entrance formula, and we had to set it up like this. We set these equal to each other. Here was your principal. Here's your 1 plus your 0.08, and to the 12t. Now, back when we did exponential equations, we said we graph this in y1, graph this in y2, or vice versa, whichever one you put it in. And from there, we can see where they intersected. Now, we're going to do the same exact thing with a log statement, because now we know how to pull down your log statement. Now, when we do this, there's a couple of little shortcuts you can take. Now, I advise only when it divides evenly. If your exponent belongs to this guy. If you can divide 3750 evenly by 1500, in other words, you don't have an irrational number, you can divide it out. Otherwise, you can put the logs on both sides and we'll do a product. So this one, it doesn't divide out badly. So we'll divide this one out. And the next one, we'll do the product thing. This will divide out to 2.5. Now you only have a one-term deal. Now, what makes that exponent come down is a power log rule. So therefore, we have to take the log of both sides. Log or ln, it doesn't matter. Bring down your 12t, because that's going to come out of your exponent. Leave this guy as it is. Just leave that mess in that parentheses. Don't resolve that, because that's probably an irrational number there. Now, just like we did with your equations, we're solving for t. Everything here is multiplied, they're products. So we're going to divide both sides by 12. We want the t there, and we want to divide by this, the log of this mess. So we're going to divide both sides by this. Now remember, we have more than one term on the denominator, so therefore, we're going to have to put parentheses around this denominator when we divide. And you'll get the same exact answer you got when we solved them exponentially in our graphs. Because now we learned how to bring the exponent down using a log function. So you're going to divide this out. Give it a try. Okay, and you should come out with 11.492, and again, this is years. This will take these many years to accumulate that much money. Did you get that? This is the same thing we did when we solved it exponentially, and we graphed it. We graphed your exponential growth, we graphed it here, and we found the intercept to be 11.492. Put it y1, y2, and we graphed it. Now, you're able to bring down your exponent using a log statement.
So on the test, do you do this version or the other version?
Well, it depends. If it says algebraically, then this is algebraically. Graphically, you can do it the other way. The test that I'm going to give you is just logs. We did the exponent, and I left it be.
Oh, so A was P and this.
Well, you will, because essentially that's this formula. 1 plus 3. That is that formula. It's just that we already developed this one. These were applications we did with your exponents. So I wanted to redo them with your logs so that you see that they work with, you'll get the same answer, but it's just another approach. Graphically, we solve them exponentially. Algebraically, we solve them using a log. Good? Okay. Let's try another one. Now remember, we solved these before, so I kind of gave you the problem that you had before. Back in your application part 2, number 4 of your applications, I took the same number out of there. We did this one. Determine when an investment doubles. If the value is 6% compounded continuously. Your continuously was your PERT. We said for it to double 2 to 1 at 06. This is what you came up with when we did this before. We graphed it. We said, okay, exponential growth, I want it to double, tell me where they intersect. Now, we can solve it algebraically because you know your power rule brings down your exponent. And because this is a base E, what do I have to use? ln. So I take the ln of both sides. I have an equation. Now you bring this out. What happens to ln E? Cancels. I have to solve for t. It's being multiplied by 0.06. So what do I have to do? Divide both sides by 0.06. Okay. So you're going to divide this out. And we should get the same exact answer that you got from your graph. Remember, I want 3 decimal places on your rounding, unless it's money. So when you divide this out, we should find this in years. Good? Are you ready when you actually get it? Okay. Good. So one we did graphically using exponential curves. The other we did algebraically using your logs. The only rule that brings down that exponent variable is your power rule. So we have to give logs to both sides. Good? Okay. One more, and then you're going to work them out. Okay. Back in your application packet that we did the second day, only I called them 1 and 2 reversed, I think. Number 2 said we had a population of a town, and it was decreasing at this rate. So we had to say principal 1 minus the rate for time. Okay, because we did the y equals ab to the x. So we started with something, we ended with something, we're decreasing our population. If you look back, you would find we had this equation. We wanted to know when it decreased all the way down to 50,000. So we started with 123,000. We decreased it by this rate over time. We wanted to know when. When was this when our population decreased at about 2.3 something percent a year, and we would get to 50,000. So we graphed it. We saw a decreasing curve, and we saw the intersect for the line, and we found it with our intersect. Now we're going to solve it with your logs. Now, this exponent only belongs to that piece right there, to that factor, not the other one. If I try to divide both sides by 123,000, it doesn't come out nicely. It doesn't terminate. And I don't want it rounded. So this one we're going to solve the long way. The only thing that will still bring this exponent down is a log. So we take the log of both sides. And actually, you can do this part in your calculator if you like. The 1 minus, you just make it a little bit easier. The 1 minus this comes out to be 0.97625. You can just do that part because that'll come out naturally. Now, here's the thing. We've said again, this belongs here. These are two factors. When I multiply like bases, what do I do to the exponents? Add them. So I have to turn this product, using my product rule, into an add statement. I have to say the log of 123,000 plus the log of 0.97625 to the t. Now I can bring the t in. Still equal to this guy. I didn't do anything to this side. So this t is going to come down here. Okay, that's what allows us to bring it down, the word log in front of it. But we couldn't separate this piece without using your product rule. Everybody see why? We couldn't multiply these two things together because the t only belongs to the 0.97625. It doesn't belong to the 123,000. So now we get this guy here. And it's like any other equation. You're going to isolate this. So we're going to subtract the log of 123,000 from both sides. You have to write this out. Log of 50,000 minus the log of 123,000 equals t log of this. Now what should we do to solve for t? Divide both sides by this log. Just like yesterday's equations. Now the only thing, before I put this in my calculator, what do I need to include? Parentheses, where? Up top in your numerator, because you're doing two things here. So you're going to, and don't forget, it also gives you parentheses around your log numbers. So you've got a couple of parentheses going on. So when you put this in, you will find your value of t to be the same thing when we did a decreasing and we intersected it to your 50,000. Exponentially, we graph it. Algebraically, we solve using logs. Anybody come up with an answer? Give me three decimal places.
37.449.
Still 450, right? So it'll take us about 37 and a half years for our population to decrease to 50,000 at 2.375% each year. We get the same exact thing as we did when we graphed it. But this allows us to bring it down. This is important right here, guys, that you realize that this exponent only belongs to this factor right here. We can't multiply these two things. We have to separate them using your product rule. So think about your exponents. What were you doing when you were multiplying like bases? You added your exponents. So turn this into an add. Logs are exponents. Turn them into an add. Isolate it. Now the other one we kind of got a little bit easier because we were able to divide that number out and only have one term. If it divides out and it terminates, by all means, do it. If it doesn't, then do it the long way. You don't want to round in between. Questions? So what you guys are going to do is you're going to go back to your packets from your applications for your exponents. I kept the same number. You're going to pull out the equation And instead of solving it graphically, you're going to solve it using logs.